Wonderful. I love it. Now gives this outcome here. So this is all well and good. Let's work with the toy example here. By evaluation. So this first, the element here in the output of C is also the first column, and 7 plus 4, which is 11. Okay, so that's very convenient. So let's swing back up here. The way much of sum, of course, is 2 multiplies t. See that this is a batch element. There will be a t by t multiply. So this will now create b by t by c. And so this, so okay, we're not going to be able to, okay, we're not going to be able to just stare it down, but well, let me try expo basically just at the 0th element and expo 2 at the 0th element. So just the first batch, and we should see that this and that should be identical, which they are, right? So what happened here? The trick is we were able to use batch matrix multiply to do this aggregation, really. And it's a weighted aggregation, and the weights are specified in this t by t array. And we're basically doing weighted sums. And these weighted sums are according to the weights inside here, that take on sort of this triangular form. And so that means that a token at the tth dimension will only get information from the tokens preceding it. So that's exactly what we want. And finally, I would like to rewrite it in one more way. And we're going to see why that's useful. So this is the third version, and it's also identical to the first and second. But let me talk through it. It uses softmax. So trill here is this matrix, lower triangular ones. Way begins as all 0. Okay, so if I just print way in the beginning, it's all 0. Then I used masked fill. So what this is doing is way.masked fill, it's all zeros, and I'm saying for all the elements where trill is equals 0, make them be negative infinity. So all the elements where trill is 0 will become negative infinity now. So this is what we get. And then the final line here is softmax. So if I take a softmax along every single, so dim is -1, so along every single row, if I do a softmax, what is that going to do? Well, softmax is also like a normalization operation, right? And so spoiler alert, you get the exact same matrix. Operation, right? And so spoiler alert, you get the exact same matrix. Let me bring back the softmax. And recall that in softmax, we're going to exponentiate every single one of these, create every single element here, where else, and then zeros. And then softmax will, again, divide, and this will give us 0.5, 0.5, and so on. And so this is also the same way to produce this mask. Now, the reason that this is a bit more interesting, and the reason we're going to end up using it in self-attention, is that these weights here begin with 0. And you can think of this as like an interaction strength or like an affinity. So basically, it's telling us how much of each token from the past do we want to aggregate and average up. And then this line is saying tokens from the past cannot communicate. By setting them to negative infinity, we're saying that we will not aggregate anything from those tokens. And so basically, this then goes through softmax and through the weighted, and this is the aggregation through matrix multiplication. And so what this is now is, you can think of these as, these zeros are currently just set by us to be 0. But a quick preview is that these affinities between the tokens are not going to be just constant at 0. They're going to be data dependent. These tokens are going to start looking at each other, and these affinities between the tokens are not going to be just constant at 0. They're going to be data dependent. These tokens are going to start looking at each other, and some tokens will find other tokens more or less interesting. And depending on what their values are, they're going to find each other interesting to different amounts, and I'm going to call those affinities, I think. And then here we are saying the future cannot communicate with the past. We're going to clamp them. And then when we normalize and sum, we're going to aggregate sort of their values depending on how interesting they find each other. And so that's the preview for self-attention. And basically, long story short from this entire section is that you can do weighted aggregations of your past elements by using matrix multiplication of a lower triangular fashion. And then the elements here in the lower triangular part are telling you how much of each element fuses into this position. So we're going to use this trick now to develop the self. attention block. So first, let's get some quick preliminaries out of the way. First, the thing I'm kind of bothered by is that you see how we're passing in vocab size into the constructor? There's no need to do that because vocab size is already defined up top as a global variable. So there's no need to pass this stuff around. Next, what I want to do is, I want to create like a level of indirection here, where we don't directly go to the embedding for the logits, but instead we go through this intermediate phase, because we're going to start making that bigger. So let me introduce a new variable, nembed. It's short for number of embedding dimensions. So nembed here will be, say, 32. That was a suggestion from GitHub Copilot, by the way. It also suggested 32, which is a good number. So this is an embedding table and only 32 dimensional embeddings. So then here, this is not going to give us logits directly. Instead, this is going to give us token embeddings. That's what I'm going to call it. And then to go from the token embeddings to the logits, we're going to need a linear layer. So self.lm head, let's call it, short for language modeling head, is nlinear from nembed up to vocab size. And then when we swing over here, we're actually going to get the logits by exactly what the Copilot says. Now we have to be careful here because this C and this C are not equal. this is an embed C, and this is vocab size. So let's just say that an embed is equal to C. And then this just creates one spurious layer of interaction through a linear layer, but this should basically run. So we see that this runs, and this currently looks kind of spurious, but we're going to build on top of this. Now, next up, so far we've taken these indices and we've encoded them based on the identity of the tokens inside IDX. The next thing that people very often do is that we're not just encoding the identity of these tokens, but also their position. So we're going to have a second position embedding table here. So self.position embedding table is an embedding of block size by n embed. And so each position from 0 to block size minus 1 will also get its own embedding vector. And then here, first let me decode b by t from idx.shape. And then here we're also going to have a pos embedding, which is the positional embedding, and this is PyTorch arrange. We're going to have a b by also get its size by n embed, so their position. So we're going to have a second position embedding table here. So self.position embedding table is an embedding of block size by n embed. And so each position from 0 to block size minus 1 will also get its own embedding vector. And then here, first let me decode b by t from idx.shape. And then here we're also going to have a pos embedding, which is the positional embedding, and this is PyTorch arrange. So this will be basically just integers from 0 to t minus 1. And all of those integers from 0 to t minus 1 get embedded through the table to create a t by c. And then here, this gets renamed to just say x, and x will be the addition of the token embeddings with the positional embeddings. And here the broadcasting note will work out. So b by t by c plus t by c. This gets right aligned, a new dimension of 1 gets added, and it gets broadcasted across batch. So at this point, X holds not just the token identities, but the positions at which these tokens occur. And this is currently not that useful because, of course, we just have a simple bigram model. So it doesn't matter if you're in the fifth position, the second position, or wherever. It's all translation invariant at this stage. So this information currently wouldn't help. But as we work on the self-attention block, we'll see that this starts to matter. Okay, so now we get the crux of self-attention. So this is probably the most important part of this video to understand. We're going to implement a small self-attention for a single individual head, as they're called. So we start off with where we were. So all of this code is familiar. So right now I'm working with an example where I changed the number of channels from 2 to 32. So we have a 4x8 arrangement of tokens, and and the information at each token is currently 32 dimensional, but we just are working with random numbers. Now we saw here that the code as we had it before does a simple average of all the past tokens and the current token. So it's just the previous information and the current information is just being mixed together in an average. And that's what this code currently achieves. And it does so by creating this lower triangular structure, which allows us to mask out this way matrix that we create. So we mask it out and then we normalize it. And currently, when we initialize the affinities between all the different sort of tokens or nodes, I'm going to use those terms interchangeably. So when we initialize the affinities between all the different tokens to be 0, then we see that way gives us this structure where every single row has these uniform numbers. And so that's what then in this matrix multiply makes it so that we're doing a simple average. Now, we don't actually want this to be all uniform because different tokens will find different other tokens more or less interesting, and we want that to be data dependent. So for example, if I'm a vowel, then maybe
Yeah, I think the one that I was saying currently, right, that here, if you see for each block size, we are just blocking out the embedding. It doesn't matter if it is 17, 58, 53, each will have its own position argument. So this would help in giving the affinity for each of them.
I'm looking for consonants in my past, and maybe I want to know what those consonants are, and I want that information to flow to me. And so I want to now gather information from the past, but I want to do it in a data-dependent way. And this is the problem that self-attention solves. Now, the way self-attention solves this is the following. Every single node, or every single token at each position, will emit two vectors. It will emit a query, and it will emit a key. Now, the query vector, roughly speaking, is what am I looking for? And the key vector, roughly speaking, is what do I contain? And then The way we get affinities between these tokens now in a sequence is we basically just do a dot product between the keys and the queries. So my query dot products with all the keys of all the other tokens, and that dot product now becomes way. And so if the key and the query are sort of aligned, they will interact to a very high amount, and then I will get to learn more about that specific token as opposed to any other token in the sequence. So let's implement this now. And then I will get to learn more about that specific token amount, and then I will get to learn more about that specific token.
Hmm. This I'm not sure why he told. I will get to learn more about that token. We'll see.
As opposed to any other token in the sequence. So let's implement this now. We're going to implement a single, what's called head of self-attention. So this is just one head. There's a hyperparameter involved with these heads, which is the head size. And then here I'm initializing linear modules, and I'm using bias equals false, so these are just going to apply a matrix multiply with some fixed weights.
So each of these um, each of the t token that we have, right, time token that we get um a head size output out of it. Thank you so much. see. Um, this is key. And the same thing.
And now let me produce a key and Q, K and Q, by forwarding these modules on X.
So for each of the token, we will produce key and query. So for each of these, sorry. So for each of these, right, this 0, 1, 2, 3, that is that C that you see, capital C, that is 32 in length. We will take it through that linear layer, and the output we'll get is head size. That is also, what is the head size? That is 16. So we should get two arrays, that small k, right? Small k equal to key x. We should get 4 into 8 into 16. That will be keys, and query will be 4 into 8 into 16. That represents query.
So the size of this will now become b by t by
Right,
16,
head size.
because that is the head size. And the same here, b by t by 16. So this being the head size. So you see here that when I forward this linear on top of my x, all the tokens in all the positions in the b by t arrangement, all of them in parallel and independently produce a key and a query. So no communication has happened yet. But the communication comes now. All the queries will dot product with all the keys. So basically what we want is we want way now, or the affinities between these, to be query multiplying key. But we have to be careful with, we can't matrix multiply this. We actually need to transpose k. But we have to be also careful because these are when you have the batch dimension. So in particular, we want to transpose the last two dimensions, dimension -1 and dimension -2. So -2, -1. And so this matrix multiply now
But here we should only look at the preceding ones, right? It is multiplying all of them. It takes the multiplication this.
We'll basically do the following. b by t by 16 matrix multiplies b by 16 by t to give us b by t by t, right? So for every row of b, we're now going to have a t square matrix giving us the affinities. And
That will be the affinity for each of them. And then we will again dot product with this masked fill again, so that we are not looking into the future elements.
these are now the way. So they're not zeros. They are now coming from this dot product between the keys and the queries. So this can now run. I can run this. And the weighted aggregation now is a function in a data-dependent manner between the keys and queries of these nodes. So just inspecting what happened here, the way takes on this form. And you see that before way was just a constant, so it was applied in the same way to all the batch elements. But now every single batch elements will have different sort of way, because every single batch element contains different tokens at different positions. And so this is not data dependent. So when we look at
That's what happens with itself. It is one, and this element with itself and the element before. So if we have seen one example, so it shows its affinity with itself. If we have seen two examples here, this is the affinity with itself, this is the affinity with before one. Same way, same way, same way.
look at just the 0th row, for example, in the input, these are the weights that came out. And so you can see now that they're not just exactly uniform. And in particular, as an example here, for the last row, this was the 8th token. And the 8th token knows what content it has, and it knows at what position it's in. And now the 8th token, based on that, creates a query. Hey, I'm looking for this kind of stuff. I'm a vowel, I'm on the 8th position, I'm looking for any consonants at positions up to 4. And then all the nodes get to emit keys. And maybe one of the channels could be, I am a consonant, and I am in a position up to 4. And that key would have a high number in that specific channel. And that's how the query and the key, when they dot product, they can find each other and create a high affinity. And when they have a high affinity, like say, this token was pretty interesting to this 8th token. When they have a high affinity, then through the softmax, I will end up aggregating a lot of its information into my position. And so I'll get to learn a lot about it. Now, just this, we're looking at way after this has already happened. Let me erase this operation as well. So let me erase the masking and the softmax just to show you the under the hood internals and how that works. So without the masking and the softmax, way comes out like this, right? This is the outputs of the dot products. And these are the raw outputs, and they take on values from negative, 2 to positive 2, etc. So that's the raw interactions and raw affinities between all the nodes. But now, if I'm a 5th node, I will not want to aggregate anything from the 6th node, 7th node, and the 8th node. So actually we use the upper triangular masking. So those are not allowed to communicate. And now we actually want to have a nice distribution. So we don't want to aggregate negative 0.11 of this node, that's crazy. So instead we exponentiate and normalize. And now we get a nice distribution that sums to 1. And this is telling us now in a data-dependent manner how much of information to aggregate from any of these tokens in the past. So that's way, and it's not zeros anymore, but it's calculated in this way. Now there's one more part to a single self-attention head. And that is that when we do the aggregation, we don't actually aggregate the tokens exactly. We produce one more value here, and we call that the value. So in the same way that we produced key and query, we're also going to create a value. And then here, we don't aggregate x. We calculate a v, which is just achieved by propagating this linear on top of x.
Okay.
Again, and then we output way multiplied by v. So v is the elements that we aggregate, or the vector that we aggregate instead of the raw x. We aggregate, and that is one way any of these tokens in the past. So that's way, and it's not zeros anymore, but it's calculated in this way. Now there's one more part to a single self-attention head. And that is that when we do the aggregation, we don't actually aggregate the tokens exactly. We aggregate we produce one more value here, and we call that the value. So in the same way that we produced key and query, we're also going to create a value. And then here, we don't aggregate x. We calculate a v, which is just achieved by propagating this linear on top of x again. And then we output way multiplied by v.
Okay.
So v is the elements that we aggregate, or the vector that we aggregate instead of the raw x. And now, of course, this will make it so that the output here
God knows why value, but And rather than directly multiplying x, we are
of this single head will be 16-dimensional because that is the head size. So you can think of X as kind of like private information to this token, if you think about it that way. So X is kind of private to this token. So I'm a fifth token at some, and I have some identity, and my information is kept in vector X. And now, for the purposes of this single head, here's what I'm interested in, here's what I have, and if you find me interesting, here's what I will communicate to you. And that's stored in V. And so V is the thing that gets aggregated for the purposes of this single. For the purposes of this single head, here's what I'm interested in, here's what I have, and if you find me interesting, here's what I will communicate to you. And that's stored in V. And so V is the thing that gets aggregated for the purposes of this single head between the different nodes. And that's basically the self-attention mechanism. This is what it does. There are a few notes that I would like to make about attention. Number one, attention is a communication mechanism. You can really think about it as a communication mechanism where you have a number of nodes in a directed graph where basically you have edges pointed between nodes like this. And what happens is every node has some vector of information, and it gets to aggregate information via a weighted sum from all of the nodes that point to it. And this is done in a data-dependent manner, so depending on whatever data is actually stored at each node at any point in time. Now, our graph doesn't look like this. Our graph has a different structure. We have 8 nodes because the block size is 8, and there's always 8 tokens. And the first node is only pointed to by itself. The second node is pointed to by the first node and itself, all the way up to the 8th node, which is pointed to by all the previous nodes and itself. And so that's the structure that our directed graph has, or happens to have, in an autoregressive sort of scenario like language modeling. But in principle, attention can be applied to any arbitrary directed graph, and it's just a communication mechanism between the nodes. The second note is that notice that there's no notion of space. So attention simply acts over like a set of vectors in this graph. And so by default, these nodes have no idea where they are positioned in the space. And that's why we need to encode them positionally and sort of give them some information that is anchored to a specific position so that they sort of know where they are. And this is different than, for example, from convolution, because if you run, for example, a convolution operation over some input, there's a very specific sort of layout of the information in space, and the convolutional filters sort of act in space. And so it's not like inattention. Inattention is just a set of vectors out there in space. They communicate, and if you want them to have a notion of space, you need to specifically add it, which is what we've done when we calculated the relative the positional encodings and added that information to the vectors. The next thing that I hope is very clear is that the elements across the batch dimension, which are independent examples, never talk to each other. They're always processed independently. And this is a batched matrix multiply that applies basically a matrix multiplication kind of in parallel across the batch dimension. So maybe it would be more accurate to say that in this analogy of a directed graph, we really have, because the batch size is 4, we really have 4 separate pools of 8 nodes, and those 8 nodes only talk to each other. But in total, there's like 32 nodes that are being processed. But there's sort of 4 separate pools of 8. You can look at it that way. The next note is that here in the case of language modeling, we have this specific structure of directed graph where the future tokens will not communicate to the past tokens. But this doesn't necessarily have to be the constraint in the general case. And in fact, in many cases, you may want to have all of the nodes talk to each other fully. So as an example, if you're doing sentiment analysis or something like that with a transformer, you might have a number of tokens, and you may want to have them all talk to each other fully, because later you are predicting, for example, the sentiment of the sentence. And so it's okay for these nodes to talk to each other. And so in those cases, you will use an encoder block of self-attention. And all it means that it's an encoder block is that you will delete this line of code, allowing all the nodes to completely talk to each other. What we're implementing here is sometimes called a decoder block. And it's called a decoder because it is sort of like decoding language. And it's got this autoregressive format where you have to mask with the triangular matrix so that nodes from the future never talk to the past, because they would give away the answer. And so basically in encoder blocks, you would delete this, allow all the nodes to talk. In decoder blocks, this will always be present so that you have this triangular structure. But both are allowed, and attention doesn't care. Attention supports arbitrary connectivity between nodes. The next thing I wanted to comment on is you keep hearing me say attention, self-attention, etc. There's actually also something called cross-attention. What is the difference? So basically, the reason this attention is self-attention is because the keys, queries, and the values are all coming from the same source, from X. So the same source X produces keys, queries, and values. So these nodes are self-attending. But in principle, attention is much more general than that. So for example, in encoder-decoder transformers, you can have a case where the queries are produced from X, but the keys and the values come from a whole separate external source, and sometimes from encoder blocks that encode some context that we'd like to condition on. And so the keys and the values will actually come from a whole separate source. Those are nodes on the side, and here we're just producing queries, and we're reading off information from the side. So cross-attention is used when there's a separate source of nodes we'd like to pull information from into our nodes. And it's self-attention if we just have nodes that would like to look at each other and talk to each other. So this attention here happens to be self-attention. But in principle, attention is a lot more general. Okay, and the last note at this stage is
Means this value relies on this, all of this. It has to predict the next token. Self-intention. Okay. I think that's what happens in the transformer. So when we give an input, so the encoder part tries to build the context or something like that and give it to the decoder where it tries to generate the next token and everything. That's how it works, I guess.
If we come to the attention is all you need paper here, we've already implemented attention. So given query key and value, we've multiplied the query and the key, we've softmaxed it, and then we are aggregating the values. There's one more thing that we're missing here, which is the dividing by 1 over square root of the head size. The dk here is the head size. Why are they doing this? Why is this important? So they call it a scaled attention. And it's kind of like an important normalization to basically have. The problem is if you have unit Gaussian inputs, so zero mean, unit variance, k and q are unit Gaussian, then if you just do way naively, then you see that your way actually will be, the variance will be on the order of head size, which in our case is 16. But if you multiply by 1 over head size square root, so this is square root and this is 1 over, then the variance of way will be 1, so it will be preserved. Now, why is this important? You'll notice that way here will feed into softmax. And so it's really important, especially at initialization, that way be fairly diffuse. So in our case here, we sort of locked out here, and way had a fairly diffuse numbers here. So like this. Now the problem is that because of softmax, if weight takes on very positive and very negative numbers inside it, softmax will actually converge towards one-hot vectors. And so I can illustrate that here. Say we are applying softmax to a tensor of values that are very close to 0, then we're going to get a diffuse thing out of softmax. But the moment I take the exact same thing and I start sharpening it, making it bigger by multiplying these numbers by 8, for example, you'll see that the softmax will start to sharpen. And in fact, it will sharpen towards the max. So it will sharpen towards whatever number here is the highest. And so basically, we don't want these values to be too extreme, especially at initialization. Otherwise, softmax will be way too peaky. And you're basically aggregating information from like a single node. Every node just aggregates information from a single other node. That's not what we want, especially at initialization. And so it aggregates information from a single information from like a single node. Every node just aggregates information from a single other node. That's not what we want, especially at initialization. And so the scaling is used just to control the variance at initialization. Okay, so having said all that, let's now take our self-attention knowledge and let's take it for a spin. So here in the code, I've created this head module and it implements a single head of self-attention. So you give it a head size, and then here it creates the key, query, and the value linear layers. Typically, people don't use biases in these. So those are the linear projections that we're going to apply to all of our nodes. Now here, I'm creating this trill variable. Trill is not a parameter of the module. So in sort of PyTorch naming conventions, this is called a buffer. It's not a parameter. And you have to call it, you have to assign it to the module using a register buffer. So that creates the trill. the lower triangular matrix. And when we're given the input x, this should look very familiar now. We calculate the keys, the queries, we calculate the attention scores inside way. We normalize it, so we're using scaled attention here. Then we make sure that future doesn't communicate with the past, so this makes it a decoder block. And then softmax, and then aggregate the value and output. Then here in the language model, I'm creating a head in the constructor, and I'm calling it self-attention head. And the head size, I'm going to keep as the same and embed, just for now. And then here, once we've encoded the information with the token embeddings and the position embeddings, we're simply going to feed it into the self-attention head, and then the output of that is going to go into the decoder language modeling, and the embeddings and the position size in value. So this makes it
So for each of those,
a decoder block. Then here in the language model, I'm creating a head in the constructor, and I'm calling it self-attention head. And the head size, I'm going to keep, once we've encoded the information with the token embeddings and the position embeddings, we're simply going to feed it into the self-attention head, and then the output of that is going to go into the decoder language modeling head and create the logits. So this is sort of the simplest way to plug in a self-attention component into our network right now. I had to make one more change, which is that here in the generate, we have to make sure that our IDX that we feed into the model, because now we're using positional embeddings, we can never have more than block size coming in, because
let's do it in the next iteration, and I will try to get the VS Code up and running with